So in this video we're going to do an example of an improper integral where the integral diverges, and we're going to be looking at the function 1 over x. So the integral that we are interested in attempting to evaluate is the integral from 1 to infinity of 1 over x dx. So we have the integral from 1 to infinity of 1 over x dx. So here's the graph of 1 over x, starting at x equal to 1 on the x-axis and going to infinity. So just like in the previous video where we were evaluating the integral of 1 over x squared, we're finding the area under the curve from 1 to infinity. We're looking at the interval from 1 to infinity. It's a half open interval. So just like we did before, we are going to replace the upper bound of integration with the variable. So we're going to take and then we'll take the limit as that variable approaches infinity. So the limit as a goes to infinity of the interval from 1 to a of 1 over x dx equals, so now we continue to write our limit notation, the limit as a goes to infinity. We integrate 1 over x. 1 over x, the antiderivative of 1 over x is the natural log of the absolute value of x, but on the interval from 1 to infinity, we don't need the absolute value sign. And this is going to be from 1 to a. We're taking the limit as a approaches infinity, so we can plug in our limits of integration. So we're taking the limit as a goes to infinity of the natural log of a minus the natural log of 1. And what we want to think about is, what is the limit as a goes to infinity of the natural log of a? And we want to remember that the natural log function sweeps up along the y-axis. The y-axis is a vertical asymptote. It sweeps up and it goes like this, and it slowly goes off to infinity. So as x goes to infinity, the natural log of x goes to infinity. So we wind up getting infinity right here. Infinity minus the natural log of 1 is 0. We input 1, we get 0. So in this case, the limit is going to be infinity, which isn't a number, so the limit does not exist, which is why we say it diverges. The limit diverges to infinity. It doesn't converge to a real number value. So even though I put it, the convention is to put infinity here when the limit goes to infinity. Even though that's the convention, the limit still does not exist because the limit needs to be a real number value. What's going on here is simply this. So in the previous video we looked at 1 over x squared on the same interval. We did the integral from 1 to infinity of 1 over x squared dx, and we discovered that this was equal to 1, whereas this turns out to be infinity. And here's the basic idea. Here's the function 1 over x, and here's the function 1 over x squared. And a necessary condition for an integral to converge is that the function has to approach the x-axis. It has to approach 0. And whether or not it converges like 1 over x squared does, or diverges like 1 over x did, what's going to determine whether it converges or diverges is the speed at which it approaches the x-axis or approaches 0. So here you see 1 over x squared approach 0 very quickly, and you can see that the area between 1 over x squared and the x-axis quickly diminishes to essentially 0, whereas 1 over x approaches the x-axis much less quickly. And so what happens is we always wind up having more and more area to add up, and that area just goes to infinity. So kind of a big idea is these functions, they need to approach the x-axis. They need to approach 0 for the integral to converge to a specific value. But that isn't sufficient. The speed at which you approach 0 or the x-axis also matters. And that's why this example showing these two integrals is kind of a classic thing to do, because the what the function behavior is similar, but you get a function that converges versus diverges.